If you've ever owned a DVD player, you'll be familiar with the oddly mesmerizing experience of watching the screensaver, where the DVD logo bounces around the screen back and forth and up and down. And all the while, you watch in anticipation of the elusive corner hit. Sometimes it comes really close and just misses, but when the trajectory lines up just right, a miracle happens. An event beautiful enough to make God himself weep. Here it comes. This is it. Oh, come on! Now, after this terrible failure, I'd like to be able to predict exactly when my DVD logo will hit the corner. And luckily, there's a way to do that, but it takes some time to explain. Meanwhile, I'll keep this logo in the background and label all the times it'll hit the corner at the bottom of the screen. Also, I've made a DVD logo simulation linked in the description that I'll use throughout this video. Given any setup of a DVD logo, it'll tell you exactly when it will hit a corner and which corner it will hit. But in order to predict when our logo will hit the corner, we first need to understand exactly how a bouncing DVD logo works. To do this, we'll build a logo from scratch. Let's start with our screen, and then we'll add our logo. Our logo has to move, so let's give it a speed. And we want it to move up and down too, so let's give it a speed along the y-axis as well. And, oops, we need to decide what happens when our logo hits the wall. When it hits the left or right wall, let's flip the direction of our x speed. And when it hits the top or bottom wall, let's flip the direction of our y speed. So now we have a working model of our DVD logo. But let's ask one more question. What does it actually mean for our logo to hit the corner? At first, the answer seems simple. It just means that the logo hits one of the sidewalls at the same time as the top or bottom wall. But how close to the same time does it need to be? Can it even be the exact same time? Well, in the real world of continuity, you'd need to be pretty dang precise in order for the logo to hit the two walls at the exact same time. Any slight offset from the perfect trajectory would mean that there's a slight difference in time between hitting one wall and hitting the other. But luckily, our DVD logo doesn't live in the real world. It lives in a discrete, computer-generated world. And our discrete world is subdivided into pixels and frames. A frame is just the smallest unit of time that exists in our logo simulation. And the speed of our DVD logo is defined as the number of pixels our logo moves every frame. And since our DVD logo only moves once per frame and can move multiple pixels at a time, that means a wall hit occurs when the logo moves up to or past the edge of the screen during a frame. And with that definition of a wall hit, a corner hit is simply when two wall hits occur on the same frame. So now we have a bouncing DVD logo, and we've defined what a corner hit is. The next thing we need to do is determine when one will occur. Using our definition, let's break down this problem into a few smaller problems. Since a corner hit requires two simultaneous wall hits, let's see if we can predict anything about our wall hits. One important insight to keep in mind as we investigate these wall hits is that the x and y components of our velocity are independent. Our motion along the x-axis has no effect on our motion along the y-axis, and vice versa. Another thing to keep in mind is that, although the direction of our speed changes, the magnitude, or how many pixels we move in one frame, doesn't. These two facts combine to give us a pretty easy way to model our logo. For our horizontal motion, we know that we move the same number of pixels every frame, and we know that our screen is a certain number of pixels wide. Therefore, we can divide our width by our speed to get the number of frames it takes to move across the screen. We can do the same thing with our vertical motion, substituting x for y and width for height, to get the number of frames it takes to move across our screen vertically. So now we have an amount of time to travel across the screen. That, of course, is the same as the number of frames between each consecutive wall hit, also known as the period of the wall hits. This means if we start our logo on the left or the right, any multiple of our period will be a frame on which we hit a sidewall. If we start at the top or bottom, the same will be true for our vertical period in the top and bottom walls. So then, to determine the first time we hit a corner, we just need to take the least common multiple of our horizontal and vertical periods. But that only applies if we start in a corner. What if we don't? Well, we can still calculate how many frames it will take before our logo hits the wall initially by dividing distance by speed, and after that, the same period applies. So we have an additional horizontal and vertical offset. Let's label our terms so far. Let's call the horizontal period t sub h and the vertical period t sub v. Then we'll call the offset k sub h and k sub v respectively. What we're looking for now is the smallest number that is kh more than a multiple of th, and kv more than a multiple of tv. Problems like these are actually a fundamental part of the field of number theory, and they're typically written in this notation. And if you've studied number theory, then you may know exactly where to go from here. Let's talk about it. One major aspect of number theory is remainders. Let's pretend we start at our left wall, and our period th is 100, meaning we hit a wall every 100 frames. And let's ask ourselves, how many frames has it been since we last hit a horizontal wall? And let's call our current frame f. If we divide f by 100 and take the remainder, this gives us the answer to our question. If f equals 105, we divide by 100 and get 1 with a remainder of 5, meaning we hit the wall 5 frames ago. If we're on frame 1250, we divide by 100 and get 12 with a remainder of 50, meaning we've hit the wall 50 frames ago. Notationally, we say that 1250 is congruent to 50 mod 100, meaning that 1250 and 50 have the same remainder when divided by 100. And the nice thing about this notation is that it obeys many of the same rules as regular algebra. Just whenever we reach the value of our period, we roll back over to 0. Going back to our problem before, asking for a number that's kh more than a multiple of th means that our number x is congruent to kh mod th. Additionally, our same number x is congruent to kv mod tv. So how do we solve a system of equations like this? Well, we could just check integers in order, but that'd take a long time. Also, what if there's no solution? We'd just keep checking numbers and never find anything. So let's come up with a better way. Let's actually take a bit of a leap of faith to solve this problem. We'll start by pretending that we have two numbers that, when multiplied by our periods, sum to 1. Now, this is a non-trivial leap, and we'll justify it later, but I first want to show you why it's a useful one to make. Once we have these two numbers, let's call them u and v. Look at our equation mod th. The left half of our equation is 0, since it's a multiple of th. Therefore, the right side of our equation must be 1. Similarly, for our equation mod tv, the right half of our equation is 0, and the left half is 1. So this expression kind of splits up the number 1 between both of our periods. And now let's try something else. We'll multiply the left part of the equation by our vertical offset, and the right part of our equation by our horizontal offset. Now our equation mod th is still 0 on the left side, but on the right side it's congruent to kh. And our equation mod tv is still 0 on the right side, but on the left side is congruent to kv. Therefore, we've just constructed a solution to our equation, a number that is congruent to kh mod th and kv mod tv. This is what's known in number theory as the Chinese Remainder Theorem. All that we need to do now is figure out how we can get our numbers u and v. To calculate u and v, let's remember our goal of writing u times th plus v times tv equals 1, where u and v are integers. To do this, we're going to take one more leap of faith and start by trying to get the greatest common factor, or the GCF, of th and tv. To do this, I want to decrease the size of the numbers that I'm working with. Let's pretend our horizontal period is 400 frames, and our vertical period is 201 frames. Any factor shared between 400 and 201 will also be shared between 201 and 400 minus 201, or 199. This is because if our GCF is a factor of 201, 201 is a multiple of our GCF. And if we subtract a multiple of our GCF, our new number will still share all of the relevant factors. So now we have two new numbers, 201 and 199. But we can apply the exact same reasoning to say that the GCF of 201 and 199 will be the same as the GCF of 199 and 2. Now, 199 equals 99 times 2 plus 1. So we know that the GCF of 199 and 2 is the same as the GCF of 2 and 1. And the GCF of 1 and anything is 1, so we know that our GCF must be 1. Or, in other words, 400 and 201 are coprime, meaning they share no factors other than 1. This process of getting our greatest common factor is called the Euclidean algorithm, and it also becomes useful for finding u and v. Under the assumption that our periods are coprime, we can actually work backwards through the Euclidean algorithm to find u and v. Let's rearrange all of our previous equations so that our remainder is on the left. Notice that the rightmost number in each of these equations is the same as the leftmost number in the equation below it. Using that fact, let's substitute our second to last equation into our last equation. Now we have 2 copies of 199, so let's distribute and add like terms. Now we have a new equation, and now we can substitute the right side of the third equation in for 199. Once we distribute and add like terms again, we get the equation 100 times 400 minus 199 times 201 equals 1. Therefore, u equals 100 and v equals negative 199. And nothing we did here was specific to 400 and 201. This process will work with any 2 coprime numbers. Looking back at our main problem, this means that any DVD setup with 2 coprime periods will eventually hit the corner. The last step before we put all this together is to ask one more question. Earlier, we assumed that our periods were coprime, but what if they're not? Well, we can use the process from before to find a u and v to write our periods in terms of the greatest common factor. From now on, let's call that greatest common factor g. If our periods are coprime, then g will be 1, and we'll always find an integer u and v. But if they're not, we can just divide by g to get an equation with 1 on the right-hand side. And we can always do that and still only have integers because g is, by definition, a factor of both of our periods. But one problem remains. Once we divide by g, our equation is no longer in terms of both of our periods, but a factor of them. Remember, the reason we want our equation to be in terms of our periods is that we can multiply by our offsets to get a number that is congruent to kh mod th and kv mod tv. If that property isn't upheld when we divide by g, then our whole effort is pointless. So with that in mind, let's multiply by our offsets and define x as we did before, but now having divided by g. And afterward, let's see if our property is upheld by rewriting our equation in terms of just one of our periods. Using our original equation, we can rearrange it to get a value of th over g times u, and plug that into our new equation. Simplifying, we get that x equals this ugly thing. Now we want the right side of our equation to be a multiple of tv, so that mod tv, x will be congruent to kv. In order for that to be the case, we need kv minus kh to be a multiple of g, so we can move it on top of tv and still get an integer when multiplied by tv. If this isn't the case, then our nice properties actually won't be upheld. In other words, if kv minus kh isn't a multiple of g, we can show that there is no solution. Why is this? Well, let's look at our original system of equations. Rearranging, we can get x minus kh is congruent to 0 mod th, or in other words, x minus kh is a multiple of th, since the remainder is 0 when you divide by it. The same goes for x minus kv. Since g is a factor of both th and tv, x minus kh and x minus kv must also be a multiple of g. Then, back in mod notation, we can move our offsets back to the right, to get that x is congruent to kh mod g, and x is congruent to kv mod g. Therefore, kh and kv must be congruent mod g. Then rearranging again, we get that kh minus kv is congruent to 0 mod g, which means that kh minus kv must be a multiple of g. If it's not, then we have a contradiction, and so we know that our equation has no solution. So looking back at our equation before, we get that x equals kv minus the quantity kv minus kh divided by g times tv times v. And since we know that our right side is a multiple of tv, we know that x is congruent to kv mod tv. And the same logic would apply to show that x is congruent to kh mod th. So now we've found a solution for non-coprime periods and the conditions under which it will work. We have the following process. First, we confirm the difference of our offsets is a multiple of g, the greatest common factor of our periods. If it's not, then we know that our setup will never hit the corner. Then we can define x as so, where u and v are our coefficients we use to write our periods in terms of g. And now we've defined a way to calculate when any DVD logo will hit the corner. Let's review. The first step is to use the size of the canvas as well as the horizontal speed and size of the DVD logo to calculate the period of hitting a sidewall. Then, we use the initial x-coordinate of the DVD logo to calculate the initial offset. Then we repeat the first and second step to calculate the vertical period. The fourth step is to use the Euclidean algorithm to determine the greatest common factor of our periods. If our greatest common factor is 1, we're good to go. Otherwise, we need to check if the difference of our offsets is a multiple of our greatest common factor. If it's not, we stop here knowing that our DVD logo will never hit the corner. Now we go backwards through the Euclidean algorithm to write our periods in terms of their greatest common factor, and we get coefficients that, when applied to our periods, sum to 1, dividing by our greatest common factor if necessary. Now, to get the first frame the corner hits, we multiply the horizontal term by our vertical offset and the vertical term by our horizontal offset. This will give us the time our DVD logo will hit the corner. Now that we know how, let's build an example DVD setup and predict when it will hit the corner. Then we can compare our answer to the one we get when actually simulating a logo. Let's use this setup on the simulation. We have a 500 by 400 pixel screen, and we start at x position 100 pixels and y position 150 pixels, with an x speed of 3 pixels per frame to the right and a y speed of 3 pixels per frame upwards. Our DVD logo is always 100 pixels wide and 54 pixels tall. Now we can start by calculating our periods. When doing so, we need to know that our DVD logo location is measured from the top left corner. To go between sidewalls, the logo has to move 400 pixels horizontally. At our speed of 3 pixels per frame, it will take 134 frames to get from one side to the other. Repeating the same process for our vertical period, we get 346 pixels moving 3 pixels per frame, and thus a period of 116 frames. For our horizontal offset, we're moving only 300 pixels before we hit the right wall for the first time, so our horizontal offset is 300 over 3, or 100 frames. For our vertical offset, we're moving 150 pixels before hitting the top wall, so our vertical offset is 150 over 3, or 50 frames. So now we can set up our equation. Our value x is congruent to 100 mod 134 and 50 mod 116. Next, we need to calculate g, the greatest common factor of our periods. Using the Euclidean algorithm, we get these equations. Since we have a zero remainder in the last equation, we know that 2 is our greatest common factor. Now we check if our offsets are equal mod g, and since 100 and 50 are both even, we know that they are. This means that we will hit the corner. Now we can work backwards through the Euclidean algorithm to find values of u and v. We end up getting u equals 13 and v equals negative 15. So, to calculate x, we just multiply 13 times 134 times 50 minus 15 times 116 times 100, all divided by 2. And that gives us negative 43,450. Oh, that doesn't make sense. Or does it? We didn't make a mistake here. Our value of x does meet the properties we set in our system of equations. It's 100 more than a multiple of 134, and 50 more than a multiple of 116. But it's not the only number that fits those properties. If we ran our simulation in reverse, then we would hit a corner on frame 43,450. So this leads us to another question. What about subsequent hits? After we hit a corner, when will we hit one again? If we can answer this question, we'll know the first positive number that meets these criteria. And actually, it turns out we've answered this question already. If we recall earlier in the video, we started with the simpler assumption that we started our DVD logo in a corner. And if we start there, then the first hit will just be the least common multiple of our periods. And the only difference between starting in a corner and getting to a corner later is which frame we're on. That means we'll hit a corner again after a number of frames equal to the least common multiple of our periods. So all we need to do is calculate the least common multiple L and take our negative solution mod L, which will yield a number between 0 and L that represents the first frame we hit the corner. We can calculate L by simply multiplying our periods and dividing by G. In this case, we get 7,772. And negative 43,450 mod 7,772 is equal to 3,182. And let's see if we're right. Perfect. Now that we've calculated corner hits, there are a few follow-up questions. The first is one we've already answered. When will we hit the corner next? Well, it'll be in another L frames, so in this case, it'll be on frame 10,954, and every 7,772 frames afterward. The next question is a bit harder. Which corner will we hit? If you saw the simulation before, you'll know that it answers this question. But there are actually two ways to calculate this. The first way uses what we've already calculated and just gets us a bit more information. In the case of the example, we know that it hits the corner first on frame 3182. If we subtract our offset of 100 frames, then divide by our period of 134 frames, we learn that the logo has hit a sidewall exactly 24 times. Once after the initial offset, then 23 times afterward. Since the logo always alternates between hitting the left and right wall, and 24 is even, and since we know that we hit the right wall first, this means we'll be hitting the left wall. If we repeat this process for the vertical period, we get that we hit a top or bottom wall 28 times. Since 28 is even, and we hit the top wall first, we know that we must be hitting the bottom wall as well. Altogether, this means that on frame 3182, we're hitting the bottom left corner. We can repeat this process for any corner hit prediction, but we actually don't have to. Like we said before when deciding about subsequent corner hits, whenever we hit a corner, the program is in the exact same state every time. So that means if we hit the bottom left corner, the top left, then the bottom left again, we know that we'll hit the top left next, then the bottom left again, etc. So we only need to calculate this for enough hits until it loops. Then we know which corners we hit and which corners we'll ever hit. Now, if this were the last follow-up question, I wouldn't bother talking about the second way. But there's actually one more interesting follow-up question, and this other method of calculating which corner we hit gives us a nice sneak peek into the solution. This method is to separate our single system of two equations into 4 systems of 2 equations, each for hitting a different corner. So instead of a period and offset for hitting either horizontal wall and either vertical wall, we'd have a separate offset for each wall, and a separate period for the side walls and the bottom walls. The period will be the same for both horizontal walls, as in each case the logo has to travel across the screen twice. Same with the vertical walls. In our case, our horizontal period is 2th, or 268 frames, and our vertical period is 2tv, or 232 frames. Our right wall offset is kh, or 100 frames, but our left wall offset is kh plus th, or 234 frames, because the logo hits the left wall for the first time, th frames after hitting the right wall for the first time. Our top wall offset is kv, or 50 frames, but our bottom wall offset is kv plus tv, or 166 frames. Altogether, this gives us these 4 equations for each of the walls. For the right and top walls, all we needed to do was double the periods. For the bottom and left walls, we both double the period and add the old period. Now, for each corner hit, we can just solve the corresponding equations. Let's start with the top left. For that equation, we get x equals negative 160,030, but mod our least common multiple, we get 10,954. Which is the first time we hit the top left. For the top right, we get these equations. Our greatest common factor of our periods here is 4, and since 100 is a multiple of 4 and 50 is not, we actually know that we'll never hit the top right. So let's do the bottom left. In this equation, both of our offsets are 2 more than a multiple of 4, so we know there will be a solution. Here, we get this number, which mod our least common multiple is 3,182, as expected. Then, for the bottom right, 100 is a multiple of 4, but 166 is not, so we have no solution. In total, this tells us that we'll hit the bottom left corner first, then the top left, and if we look at the consecutive hits by adding the least common multiple of our doubled periods, we can see every consecutive hit as well. We also know that we'll never hit the bottom right or top right walls. This second way of answering leads us nicely into our final follow-up question, which also ends up being the most interesting. Which sets of corners can a DVD logo hit? In our example, we only hit 2 corners. Can we set up a version that hits no corners, 1 corner, all 4? Let's start with the easiest answer. We can make a logo that hits no corners. We simply need a logo that will retrace its own steps before hitting any corners. Here's a simple example. In playing with the simulation, you may have noticed something that I noticed when testing it. Every logo that I tried would either never hit a corner or would hit exactly 2 different corners and go back and forth between them. I kept trying to make a logo that would hit all 4 corners, but I soon realized it's actually impossible. This is because whenever a logo hits a corner, it goes back in the exact same direction it came with the exact same velocity. This means that after hitting a corner, the entire motion up to that point will be entirely reversed. So if you hit corner A and then corner B, the motion will be reversed until you hit corner A again, then until you hit corner B again, and so on. This rather simple argument completely rules out hitting 3 or 4 corners. We've seen examples of 0 and 2 corners, but what about 1 corner? Hitting 1 corner means hitting the same corner twice in a row. At first, it seems pretty straightforward to construct an example that just goes straight back and hits the corner it started from. But my attempts to do so always ended up hitting another corner as well. After a lot of attempts to make a single corner hit, I grew to suspect that hitting only 1 corner was also impossible. The proof here is a bit more complicated than the proof for 3 and 4 corners, but we've actually already done a lot of the work. The first step is to separate our system of equations for hitting any corner into the 4 systems of equations for hitting each corner. Luckily, we did that earlier in the video, so we can just copy down what we wrote before. Notice here that everything is still written in terms of th, tv, kh, and kv, which are defined in the same way as for calculating any corner hit. Note also that the greatest common factor in our equations for each individual corner isn't g, but instead 2g. If g is the greatest common factor of th and tv, then the greatest common factor of twice those periods will be 2g. Also notice that these systems are dependent on the assumption that we hit the top wall before the bottom wall and the right wall before the left wall. However, if we hit a different wall first, we'd end up getting these same equations but for different corners. So it turns out we can assume this system of equations without any loss of generality. Recall that if our offsets are congruent mod g, then we know that the system is solvable. So from each of these systems of equations, we can construct a single equation mod g that tells us whether the corresponding corner will be hit. If our theory is correct, then if we assume at least one of these equations is true, then exactly 2 will be true. Any more would mean that we hit more than 2 corners. If only 1 can be true, then we know we're wrong and we can hit only 1 corner. We already know from before that if kh is congruent to kv mod g, then the logo will hit at least 1 corner. So let's keep that in mind as an underlying assumption. Now, using this assumption and the 4 equations we've set up, we want to know that exactly 2 of these equations must be true. To do so, let's try to learn what we can about our values of th and tv in different moduli. Since g is a common factor of th and tv, we know that both th and tv are congruent to 0 mod g. This means that mod 2g, th and tv must be congruent to either 0 or g. This means that there are 4 cases to consider. Let's go through them one at a time, starting with the case of 2 zeros. This case is actually impossible, because if they're congruent to 0 mod 2g, that means each of our numbers is a multiple of twice their greatest common factor. But if they're both multiples of 2g, then 2g must be a common factor of the 2 periods, and since 2g is greater than g, g can't be their greatest common factor. So that leaves us with 3 other cases to consider. Either one of our periods is congruent to g and the other 0, or both are congruent to g. All of these cases can be pretty easily shown to be possible. Now, for each of these cases, we can take our 4 equations and show that exactly 2 are true. Let's start with the first case, where th is congruent to 0 and tv is congruent to g. Now, for each of our equations, let's make the appropriate substitutions. We can see pretty easily that our first 2 equations are equivalent, and so are our second 2, which means that 0, 2, or 4 of these equations must be true. First, let's show that all 4 cannot be true. If we assume all 4 are true, then we can substitute our third equation into our second to see that kv is congruent to g plus kv mod 2g, which would have to mean that g is a multiple of 2g, which isn't possible. Therefore, all 4 being true is impossible, so either 0 or 2 must be true. And since we assumed that kv was congruent to kh mod g, then mod 2g we should see that either the 2 are still congruent, or one is congruent to the other plus g. For our next case, we end up getting these equations, and we can show exactly 2 must be true by the same argument. For the third case, we end up seeing that our first and fourth equations are equivalent, but our second and third don't immediately seem to be. Turns out though, since we're operating mod 2g, adding g is the same as subtracting g. So if we add g to both sides in our second equation, it ends up being equivalent to our third. So by this argument, no DVD logo setup can hit only one corner, since all must hit either 0 or 2. We've already shown that 3 or 4 corners were impossible, but this proof also shows that fact to be true. And you may also notice that the 2 corners we hit are arbitrary. Any set of 2 corners should work. And that's the last follow-up question. Thanks for watching. This has been a huge project for me, so thanks for sticking through to the end. I have the link to the logo prediction tool as well as the source code for it in the description. Make sure to check those out if you're interested. If you're unfamiliar with this channel, I post a ton of different projects here. Some are math projects like these, others are game development, and some are unrelated entirely. But if you like this, make sure to stick around for more, as I'll definitely do more math content in the future. Now before I go, I want to leave you with one more challenge, one that I haven't solved myself. The final proof in this video that hitting a single corner is impossible is, though rigorous, inelegant in my view. I spent a long time searching for a simple logical reason a logo couldn't hit only one corner, something as simple as the reversed motion explanation for hitting at most 2 corners. So if anyone can offer an easier explanation for a single corner hit than what I gave, I'd be thrilled to hear it. Bye!